All flip-flops and flip-flop latches share the same control signals. The group of associated control signals with a flip-flop is important since only flip-flops that share the same control signals can be grouped into the same slice. This means that if you don't manage the use of your control signals and try to reduce the number of control signals your design has, then you might have trouble getting high device utilization. The set and reset signal can be configured as synchronous or asynchronous. For synchronous design purposes, Xilinx recommends that unless absolutely necessary, your design should use a synchronous set or reset rather than an asynchronous one. We discuss good synchronous design practices in the Essentials of FPGA Design course. To help designers with this, we have made a series of Virtex-6 and Spartan-6 HDL coding style RELs. They discuss the impact of this and provide you with many good design practices that will help you get high performance and high device utilization. So check these out. Many, but not all LUTs in the FPGA can be configured for distributed RAM. This is a small 64-bit memory that can perform a single, dual, or quad port memory. Each port has independent address inputs and has a synchronous write and an asynchronous read. There are 4 configurations, as you can see from the slide. Most customers use these resources for DSP applications. Sometimes customers try to build larger memories out of these. It is possible, but the extra logic to connect these small distributed memories together make their performance prohibitive. So you may want to consider building a larger memory instead with using the dedicated block RAM resources. In general, those customers that build with this are using the core generator or the system generator to build their DSP application. Many LUTs can be configured as a 32-bit shift register as well. This is used primarily as a pipeline delay element for balancing pipelined applications, but it can also be used for variable length shift registers, synchronous FIFOs, CAMs, or for pattern generators. It is a cascadable resource that allows it to be cascaded to up to 128 bits in length. The most challenging thing with this is that most customers don't realize that it is not loadable, has no reset functionality, and only offers serial in, serial out capability. So if you try to infer it with any of these behaviors, your synthesis tool will instead infer regular flip-flops. And of course that will be a big waste if you're building a large component and expecting the shift register LUT to be used. The benefit of this resource is that it can effectively provide the work of 32 registers with a single lookup table. And in pipelined applications, that is a huge savings. This is an example of the use of the shift register LUT. The SRL can be used, as I mentioned, as a programmable delay element, or no operation, no op. In this example, you see a 64-bit bus being processed through operation A, B, and C. A has a delay of 8 cycles, B has a delay of 12 cycles, and C has a delay of 17 cycles. Because the data processed is also grouped at its output with a multiplexer, these data paths must synchronize so that the appropriate data is compared at the multiplexer. To do this, the shift register LUT can be used to delay the C operation by 9 clock cycles. If we were to do this with regular registers, it would require 576 flip-flops. If we use the SRL functionality instead, we only need 64 LUTs, each programmed for 9 clock cycles of delay. So this example uses 64 LUTs to replace 576 flip-flops, and the associated routing resources to complete this. Pretty good justification for using the SRL, huh? Because there are so many registers in FPGAs, pipelining is an effective way of designing to increase design performance. Because pipelines can sometimes become unbalanced when too much logic must be generated, it is necessary to delay some of the signals. One of the best uses of the SRL is to add delay to balance those pipelines. So now that we know that each LUT has 3 different configurations, logic, distributed RAM, and the shift register LUT, we can discuss the 2 types of slices in Virtex-6. There is the SLICEM, which is the full slice, and is about 25% of the available slices in your device. In this case, the LUT can be used for logic, memory, and the shift register LUT. It also has access to the wide multiplexers and the carry chain. The rest of the slices are slice L, which are logic and arithmetic functionality only. So the LUT can only be used for logic. There's no distributed memory resource there. It also has wide multiplexers, and of course the carry chain is associated with it. Most customers don't use as many LUTs for distributed memory or even the shift register LUT as you might think. So this segmentation of functionality does not usually have a performance impact, but instead will save transistors for other purposes that will be more beneficial to the designer. Also keep in mind that the implementation tools will lay your design out onto the die, so understanding which slices are an M or an L is not important. All we wanted to do was explain that they are different and show you how they're different. The input-output blocks, or IOBs, interface between the FPGA and the outside world. IOBs are grouped into I/O banks, which are located in columns throughout the device. IOBs contain registers and some specialized resources, but the main purpose of the IOBs is to clock data into and out of the FPGA. In fact, using registers to clock data in and out of the device is the fastest way to move data, by running it through the IOB registers. Besides registers, the IOBs contain interface logic that is designed to translate the internal voltage domain of the FPGA to whatever I/O standard you're using. This saves you from having to add all the necessary interface logic outside the FPGA. Now this requires that each bank share a common power supply for inputs called VREF and outputs called VCCO. These voltages vary by I/O standard, but Virtex-6 supports many I/O standards. Fortunately, many of these standards can share the same power supplies. Now Virtex-6 has between 9 and 30 I/O banks, depending on the device density, and each I/O bank has 40 I/O pins associated with it. The Versatile Select I/O resource was first introduced with the Virtex family of FPGAs several years ago. It has been enhanced with every new product family ever since. I/O standards have been added and selected to support what our customers require. Virtex-6 FPGAs support over 40 I/O standards, including those you see listed here. But check your datasheet to see if your I/O standard is supported. Note that there are memory-specific standards of varied classes, differential standards that require 2 I/O pins to receive the signal. The differential signaling standards include LVDS and LVPECL. The signal-ended I/O standards include LVCMOS, SSTL, and HSTL. The Select I/O feature allows direct connection of the FPGA pin to external signals of varied voltages and thresholds. This optimizes the speed-noise trade-off and saves you from having to place interface components onto your board. All the dedicated interface logic already exists and can be selected on a pin-by-pin basis. However, note that to mix different I/O standards into the same I/O bank, you must be aware of the I/O banking rules. These rules apply because each I/O bank shares power pins for each of the input and output pins in the bank. Specifically, the VREF powers the input circuitry and the VCCIO pin powers the output circuitry. So whichever I/O standards you group into each I/O bank, make certain that the input pins can support the same VREF and the output pins can support the same VCCIO. Now, as an FYI, this is easily planned by using the pin ahead utility included with the ISE software. This slide is just trying to show you how differential pins work in Xilinx FPGAs. Each pin in the device can be figured as single-ended or differential. But note that if the pins are going to be used as differential, you have a pre-assigned pair for each pin associated with the package. Note that these limitations have an impact on your pin layout, so if you're planning on using differential I/O standards, make sure that you lock your pins appropriately. And be sure on planning to lay out your design by using the pin ahead software.